Hey everyone, in this video we will talk about a simple project or a simple design project which has been requested before by a client. Okay, so no, I didn't do this project, but I have seen on one of the freelancing websites that a client wants someone to do this in MATLAB Simulink or any other simulation program. So if you look at this design project here, you can see that it says use any appropriate software in order to design a fault detection scheme using under or over voltage relay for a three-phase grid connected load in a low voltage distribution network. So what we do here is that we need to design a fault detection scheme. So if there is an over voltage or under voltage, the circuit breaker will be opened and protect the system. So as you can see here, if you look at here, this is a system that we would like to design. So as you can see, we have three-phase system, a three-phase supply, and we have the grid bus measurement. Here we have measurements that will measure the output voltage and current. Then we have here the grid impedance, which is the impedance of the transmission line. Then we have at the end, we have a circuit breaker that will protect the load. And we have here the measurement, the bus that will measure the voltage and current across the load. And the short circuit will happen across the load terminal, three-phase, three-line to ground fault occurring at this bus bar here. Okay. So we have the circuit breaker which will protect the system, and this is the fault scheme. Now if you go back here, you will see that the requirements. We need a three-phase fault to occur at the load side between 1 to 2 seconds. So we need at a time between 1, the fault will start, and end at time equal to. When the root mean square voltage during the fault period exceeds 253 or drops below 207, the fault detection scheme will detect the fault and the circuit breaker will disconnect the load. So here we have the measurement here, right? Measurement for the voltage and current. So if the voltage here greater than the RMS value of the fault here exceeds 253 volt or less than 207 volt, then what are we going to do? The fault detection scheme will detect the fault, and the fault detection will give a signal to circuit breaker to be opened. Okay, so you can see status closed, so it is normally closed, and you will give it signal from outside. Now the expected results are the following: for the trip signal, the load RMS voltage, load current, and load 3 voltage, load 3-phase voltage. Okay, so what we are going to do, we are going to add these components in MATLAB Simulink. So first we will make a new Simulink model like this, blank model. Okay, then we are going to add first power. Okay, power GUI block. Okay, like this. And then we need first what we need to go to the settings here. Okay, and data import and export, and make it not a single output. Okay, here apply and okay. Okay, this is to give us different variables in the workspace for each array, as you will see right now. Okay, so the first thing we need three-phase supply. Okay, so we need AC voltage source, AC voltage source. Let's zoom in. Then Control R to rotate like this. Okay, then Control and drag to duplicate this source. Okay. Then we will connect them like this. Okay. Then we need ground. Okay, we need ground. The ground here is the one which is specialized power systems. This one, like this. Okay, so this is a neutral. This is a three-phase Y connection grounded. Y connection grounded. Okay, now let's look at here. So we have a three-phase, each one magnitude root 2 multiplied by 230. Okay, this is the magnitude. Okay, so let's go like this and choose our calculator here, like this. So we have root 2 multiplied by 230. Okay, this is a phase voltage. Phase voltage, okay? Phase voltage as a magnitude, the magnitude of each of these supplies. So it is 325.269. Okay, couple like this and go here. Okay, like this, the peak value or the magnitude. Okay, go here, paste. Okay, go here, paste, and okay. Second thing we have here is frequency 50 hertz. So we will go here, make this one 50, copy it like this, go here, okay, 50, okay, go here and 50 hertz. Okay, so we have three-phase supply, each one with the same magnitude or same peak power or a same peak voltage, and we have the same frequency, which is 50 hertz. Now we need the phase shift, 0 minus 120 plus 120, which is the three-phase A, B, C. So it will be here phase 0 degrees, okay. Second one, negative 120 degrees. And this one with 120 degrees, okay. So we have our three-phase voltage. Then we need the measurement here, okay. So three-phase, okay, we'll say three-phase measurement, okay. Three-phase VI measurement, like this. Okay, so it will measure the three-phase voltage, like this. Okay, so the input, we can rotate this one or flip it like this. Okay, flip, rotate and flip, look, left and right, like this. So this is the input, okay, like this. Okay, this is a three-phase measurement. Okay, we can remove this, use a label and use a label, okay, like this, to remove these two output signals. So if you would like to see the three-phase voltage and the current, this is the label that you can use. This is a variable in which the values will be stored, okay. So we have the three-phase measurement. Okay, what's next? We have the grid impedance. Here is the grid impedance in the three-phase RLC. So three-phase RLC what? Three-phase series RLC branch. The branch will give you the values in resistance in ohms, inductance in Henry, capacitance in farad. For the RLC load, it will give you values in kilowatt, in kilovar, in kilovolt ampere, or in kilovar also for capacitance. So in order to, so here the requirement is what? The requirement is in ohms and Henry. So we will use the branch like this. Take this one here, and this one here, like this. Okay, go here. Then we have RL, which is the resistance and inductance of the transmission line. We have here 0.5, okay, 0.5 ohms, like this. And what's the value of inductance? 0.001. Okay, so 1, 2, and 3. So it will be 1 multiplied by e to the power negative 3. This means that 1 multiplied by 10 to the power negative 3. Okay. Okay, what is next? We have the circuit breaker, so it is a 3-phase breaker. Okay, so what are you going to do? 3-phase breaker, which is this one. Okay, connect A with A, connect A, B with B, connect C with C, and the initial status, you can see that here, status, close the status, which is the initial state of the circuit breaker. It means it is normally closed. So I'll make this one normally closed. Okay, and when we give it a signal, we will switch what? We will switch A, B, and C, the 3-phase. So we have a 3-phase circuit breaker that will control A, B, and C. Okay, these values represent the breaker resistance, or on resistance when it is turned on, snubber resistance, and so on. This value is related to the circuit breaker itself. Okay, we don't change anything of these. Here you can see that the switching time will be external, so it will give the switching signal from outside here. Okay, so we'll make the switching time or the switching signal external and apply. So you can see the switching signal is right here. Now another thing you can see is this 3-phase circuit breaker. This implements a 3-phase circuit breaker. When the external switching time mode is selected, a Simulink logical signal is used to control the breaker operation. So what does this mean? So when the circuit breaker takes a signal of 1, this circuit breaker will be closed. If it takes 0, it will be opened. Okay, logic signal. Okay, now we have also a measurement bus, so we can take this one, copy here and paste like here. Okay, so we have A like this, A, B, C. Okay, here we have what is its label. Its label will be VABC2 and IABC2. So VABC, let's say 1, okay, and this one is VABC2. So this one measures what? Measures the phase voltage and the phase current. Okay, now let's go here. So we have here the 3-phase load 10 kilowatt. So what we are going to do, we are going to say 3-phase. So this is a 3-phase with only a resistor. Okay, so you can say RLC. Series or parallel will not change anything because we have only a resistor. So let's say series RLC load because we can change it or add the values in kilowatt like this. Put A here, put B here, and C here. Then we will go here and first Y grounded, similar to the configuration of the 3-phase Y configuration, neutral grounded. So it is Y grounded. So what is the nominal phase to phase voltage? Okay, phase to phase, here this is the peak value. This one is the peak value. So in order to get here we need phase to phase RMS. So the RMS value is 230. This is the root mean square value, 230. And since we are talking about line to line RMS, so it will be multiplied by root 3. Okay, root 3. So it will give us 398.371 like this, and go back here like this. So this one 230 represent what? Representing the root mean square or phase root mean square value. If we need line to line, we take this value and multiply it by root 3 as we just did here. Okay, so we have here our load, and this is a 10 kilowatt. Okay, 10 kilowatt. Frequency 50 hertz. Don't forget about the frequency. Inductive, capacitive are 0. We don't have any capacitance or any inductance. The active power is 10 kilowatt. Okay, then apply and okay. So now we have our system. The only thing remaining, which is the three-phase fault. Okay, three-phase fault. Okay, like this. So Control R like this, or not Control R like this. Keep it like this. Right click, rotate and flip, then flip, look, left and right, Control and I. Okay, Control I. Okay, take A with A, take B with B, take C with C. Okay, like this. Now this three-phase fault, if you go inside it, the initial state, is it 0 or 1? It is 0. We don't have any kind of fault. Now what kind of fault you would like? I would like a fault between A, B and C and ground, which is real line to ground. Let's say, for example, if you would like to get line to ground, then you will say, for example, between A and the ground, then you will remove this 2. So A ground means line to ground. Then we have the switching time. When does the fault occur and when does the fault end? If you look here, the fault will start at 1 second and end at 2 seconds. So we will start at 1 second, like this, okay, and end at 2 seconds, like this. Then you have other parameters such as fault resistance, ground resistance. I usually keep them as it is, okay? Then okay. Okay, so what is the next step? So we have added all of our components in our system. What we need to do is fault detection technique. Okay, so before we go to the fault detection, what we need is the waveforms here. So we need the load RMS voltage. Okay, the voltage RMS, which is here, VABC2, as an RMS value. So I will take from like this to take the value from here, from VABC2. Remove this A like this. So what does it do? It will take the three-phase measurement, which is added in VABC2 in this variable, and it will be inside this from tag. Okay, now what I would like to do, I would like to see the RMS, the load three-phase voltage, as it is. Okay, so we can add here a scope like this. Okay, like this, to see the three-phase measurement. And I would like to see what also? I would like to see the RMS value. So I would like to do like this, RMS, root mean square. And not this one, but this one, electrical specialized power system sensors and measurement, this one. Okay, the RMS value. What is the frequency? 50 hertz. What is the initial RMS value? Here our RMS value is 230 volt. Okay, 230 volt. Okay, apply like this. So to measure the root mean square value, and then duplicate this one, control and drag like this. So we have the root mean square measurement, okay, and the three-phase measurement. Okay, what else we need? We need also the load current. So we need the three-phase current measured here. So the current is also stored at IABC2. This is the value at which it will be stored. So I'm going to add from like this and add the current like this. Okay, like this, and add another scope. Okay, we need to measure the three-phase current. Three-phase current, root mean square voltage, and the three-phase voltage. If we get back here, three-phase voltage, load current, and load RMS. Now leave the trip signal for now. Okay. Okay, now what we would like to do is fault detection scheme. So what we would like to do, when the RMS voltage during the fault period exceeds this or drops below this, we need the fault detection scheme to start working. Okay, so first let's translate this. The RMS voltage, which is this one, RMS voltage, this one. So let's make it as a tag, or go to, okay, like this, and remember, make the tag visibility global, because if we have any any subsystems, this one will work inside it. Okay, so we have to call this one V RMS like this, and okay. So this is representing the voltage RMS. So we need to look at voltage VRMS exceeds or drops. Okay, so VRMS like this, from like this, like this, Control V, apply. Okay, so this is our voltage. If it is what exceeds 253, so it is greater than or equal, whatever. Okay, like this value greater than what? Greater than 253. Okay, so constant like this, 253. Okay, then the second condition, drops below 207. Okay, less than or equal like this. So if the root mean square drops below what? Constant drops below 207. Okay, 207 like this. So we have this first condition, if voltage greater than 253 or voltage less than 2073, I would like the circuit breaker to be opened. Okay, so we need this condition or this condition. So we will add OR function like this, and it will take OR from here or from here. So remember, the circuit breaker will be opened when the signal here becomes 0. Okay, when the signal becomes 0. Okay, so can I add this directly like this? No. Why? Because if voltage greater than 253, the RMS greater than 253, it means it will give it 1. So the circuit breaker will be closed, not opened. Okay, so we need, when these two conditions are fulfilled or any of them are true, we have to give 0 signal, not 1. So what I'm going to do is add a not here to reverse this condition like this. So let's say, for example, if VRMS is greater than this value, okay, it will give us 1. So when it gives us 1 and inverted, it will give us 0. Okay, if these two are false or 0, it will give us 1. So circuit breaker will still be opened. Then we will make this like this, and what? Right click, create subsystem from selection. So if you would like to put them in one block, and call this fault detection. Okay, you can also add here, add this one, scope like this here. Okay, trip signal. Okay, why this one is the trip signal? Because if any of these conditions is fulfilled, it means it will give us 1, similar to here. When the fault occurs here, the voltage is reduced, so the signal will become 1. So this is equivalent to this part. However, in reality, trip signal of 1, if it is applied to the circuit breaker, it will close it, not open it. Okay, that's why we need to invert the signal, because when these conditions are fulfilled, or any of them are fulfilled, it will give us 1. By inversion will give us 0 and close the circuit breaker. So let's keep this as a trip signal here. Okay, like this. Get back here, and this is the RMS. Okay, V RMS, like this. Okay, like this. Then we go back here, and this one is VABC, VABC, the 3-phase voltage, like this. Okay, and here let's say IABC. Okay, so let's run this model first and see if everything is fine or is there some error. First, you need to put this one in accelerator mode, and the simulation time will be 2 seconds. Okay, let's run this model and see if everything is fine or not. Okay, so after running this simulation, it gives us an error actually. So if you look at here, it is saying error in port widths or dimensions. So here it seems there is a problem with this one. Okay, you can see here and here. So I think this one is the one which has a problem. This one measures the RMS of one signal, if I remember correctly. So this one is not the correct one. RMS statistics. This one is the one which is correct. Okay, so we'll go here like this and here. Okay, so it measures the RMS. Okay, so let's run once more and see if this fixes the problem. Okay, it actually fixed it. Warning. Okay, so let's look at the results. So the first thing we need to look at is the RMS voltage. About these values, and drops it to 0. Okay, so let's look at here. RMS, VRMS. Okay, then drops to 0, so it is correct. Second one, which is the load current, you can see a value, then boom, and goes to 0. Okay, so let's look at here. At this one, you can see current moving constantly. Okay, so you can see between 0.8 and 1.2. Okay, between 0.8 and 1.2, so this region. Okay, so if you look at here, you can see that the current was continuously or in normal condition, and here when we have the fault, the current will go crazy, then go back to 0 after switching off the circuit breaker. Okay, goes to 0 like here. So it is normally, then goes very high and drops to 0. For the 3-phase voltage, normally and have 0, like this 3-phase voltage, and then goes to 0. Okay, what else? We need the trip signal. 0, then boom, 1. Here 0, then goes up to 1. Okay, so this was an example on the fault detection. How can you add a fault detection scheme over voltage and under voltage to the system or any system you have. Okay, so I hope this lesson was helpful for you in understanding more about Simulink.